Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Yossi Oren visiting us from Tel Aviv University. He'll speak to us about the Mechanical Cryptographer. Thank you.
Fine, okay, so I'm going to talk to you about the Mechanical Cryptographer, which is a bit of a pretty exciting thing that we did in our group in the previous few months, and I think it's really interesting, and I hope to share the excitement with you. Okay, so first of all, a bit about me. I'm part of the Cryptography Network Security Lab in Tel Aviv University. And among other things we do in our lab, we research SCADA systems. We do some foundations of cryptography work, RFID work. Personally, my interests are secure hardware, which means power analysis, ways to attack using power analysis, both applied work, lab work, and both theoretical work. And low resistance cryptography for lightweight computers, particularly RFID tags. And other things I do are cryptography in the real world, which are voter privacy, web application security, and so on. Specifically today, I'm going to talk about power analysis and other hardware attacks, and specifically about a type of power analysis attack which is very unique in its application. Specifically, it can be used where previous forms of power analysis were unusable. It needs much less data, and it can be much more versatile. Okay? Things which I did where are not related to the academic, but might be interesting for you. I did a lot of coding in my life. I was both a technical leader and a program manager and a project manager. I know it's different things here in Microsoft. And I also wrote some comedy. Might be apparent in the talk. Depends on you. Okay. So I just want to calibrate people here might be from different backgrounds. Who here knows what a flip-flop is? Wow. Not the shoe, right? Who here has ever touched the scope? Okay. Who knows what AES looks like from the inside? AES. AES. Okay. Okay. So, okay. So here is the Aes Cipher, okay? The structure of the Aes Cipher, the uses of the Aes Cipher. You get plaintext on the top, you get ciphertext on the bottom, you get key, and what's inside? Bit flipping, bit shifting, permutations, and so on. This is a very efficient algorithm, okay? Modern CPUs can do 2 to the 31 AES operations per second. Very efficient, okay? So if I give you the plaintext and the key, it's very easy to do encryption. If I give you the ciphertext and the key, very difficult to do decryption. Yes, Gidon?
31 is 2 billion, and the chip is 2 gigahertz.
AES-NI. AES-NI. Multi-core.
Multi-core, sorry.
Okay, yeah. You have to do you have to cheat a bit, but in terms of how many times per second the AES-NI core is invoked, okay? Okay, so if I give you the ciphertext and the key, plaintext is easier to calculate. On the other hand, if I give you the plaintext and the ciphertext and the key is not given, it's difficult to calculate, okay? Why is this so hard? Well, this is what cryptography, this is why the cipher was designed this way. It's designed to be difficult to do cryptanalysis. Plaintext and ciphertext do not lead to the key. And what this means essentially is that there is no efficient way to represent the key as a function of the plaintext and the ciphertext, okay? In fact, most random functions which have 128-bit inputs or 256-bit inputs and 128-bit outputs are very difficult to represent, most random functions. So if you have a very difficult to represent function, you can do either two things. You either spend a lot of space, you create a huge lookup table, or you can try the efficient thing, which is known key and known plaintext, ciphertext, and just go over it a lot of times until you find the pair you're looking for. This takes a lot of time. So it's either huge space, a long time, or some sort of trade-off between the two, which is inefficient. But anyway, there is no efficient way to represent the key as a function of the plaintext and the ciphertext. Okay, I just want to put this in the side. We're going to go into this a bit more in the future of the talk. Okay, so let's put AES to the side for a moment, and I want to talk to you about a nice software tool or software machine called a solver. Who here has ever delved into solvers, tried to use a solver in your work? I know that MSRC is actually writing a solver, so you can talk to them. A solver, as it's defined, is designed to solve stuff. Okay, how do I use a solver? I input into the solver a set of statements over variables written in some sort of logic language. There's no real restriction on what language I can use. I can use SAT statements. I can use conditional logic statements. I can use English. I don't know. Okay? And the solver, upon receiving the set of statements, runs for a short while or a long while. Yeah? And then it outputs a satisfying assignment for this set of statements. Okay? It outputs the set of variables which can be assigned to this statement such that all of them are satisfied. This is a very useful tool. It's very general purpose, very versatile. One example I can give to you, which it is used for, is scheduling, for example, doctors' assignments. Okay, let's assume I have a set of doctors and a set of assignments, and the doctors have constraints. What are the constraints? For example, a doctor cannot be present at two different stations at the same time. Okay, right? Because it's a classical doctor, not a quantum doctor. And the doctor would like to sleep 6 hours per night. Okay, perhaps he would like a day free, or this doctor can't do Saturdays, and so on. Okay, so the set of statements is given to, and the variables would be Dr. Cohen is doing ophthalmology on Thursday, and so on. So the solver will output a satisfying assignment, which is the way to assign the doctors to rooms. Similarly, the way to assign postdocs to universities, and so on. Another thing which is very a common application of solvers is verifying hardware designs. Okay, hardware design, you start with a high-level language, and you end up with actually a picture which is burnt onto silicon. And some parts of this process leading from the hardware design to the silicon are manual. Some places are prone to errors. So what you do is you give the solver both the high-level definition and the actual netlist, which is so-called, this is a low-level description, and you tell the solver, is there an assignment of inputs which is different, which leads to a different output if I feed it to the high-level design, if I feed it to the silicon, okay? These are solvers, okay? Solvers are very versatile. So one of the things people thought of doing is, let's try to do cryptanalysis with solvers, okay? I'm just going to tell you what cryptanalysis is again, okay? I am going to take this crypto algorithm, for example, AES. I'm going to write the set of statements which is as follows, okay? The plaintext is P. The ciphertext is C. The transformation between plaintext and ciphertext is this set of logical expressions. And please give me the cryptographic key. This is the assignment I want to the variables. The cryptographic key will satisfy the set of statements. What this means is if I take the plaintext and encrypt it with the key, I will arrive at the ciphertext. This is exactly cryptanalysis, okay? And that would be really cute if we could just give this problem to a computer and come back tomorrow and get the key, right? So this was tried in the year 2000 by Masaki and Mararo. 2000 AES was not live yet. They used the DES. And what they found out is that, not surprisingly, of course, modern crypto is strong enough to resist solvers, okay? Obviously, you would have heard about it if it was successful. So what does this mean? You give the solver the plaintext and the ciphertext and the key, and the solver runs for an intractable time, okay? And the solver takes an unreasonable amount of memory. They just ran it for a while, and then they said, okay, we give up. We don't have enough hardware. Why is this so? Okay, we feel it. We feel that it should be so, but why is it so actually? If any of you have done some symmetric cipher design, you know that one of the most crucial elements of a symmetric cipher is what's called the diffusion property, or the avalanche property. What this means is that if I change one bit in one of the inputs, very quickly it's going to affect half of the outputs. Okay, one bit flips in the input, half of the bits flip in the output. And this happens very quickly. So AES has 10 rounds. If I change a bit in one of the rounds, in 2 or 3 rounds, all of the bits are going to be affected. So effectively, what the solver is trying to do is trying to find a candidate assignment So it's guessing, okay, let's say one of the bits of the key is 1. And then it has to propagate this belief and see if it makes all of the rest of the statements satisfiable. And as soon as it changes one of the statements, all of these other assignments become invalid because of this avalanche property. So the solver is reduced to actually brute forcing all of the keys, trying to find if one of them satisfies the relationship between plaintext and ciphertext. Okay, so it's established at this point that classical cryptanalysis using a solver is difficult. And the reason is diffusion. So, okay, I'm an engineer, and when I'm faced with a difficult problem, what I do typically is I solve a different problem, right? This is what engineers do, okay? So let's try to change the problem in a way which makes solvers more efficient, okay? So this is a definition of cryptanalysis in the sense that I'm going to use today. I am given a description of an algorithm, plaintext and ciphertext. I want to output the key. So what can I do to make this easier for me, the engineer? Okay, so first of all, I'm going to take this AES algorithm and replace it with a concrete AES device, okay? This could be a smart car, this could be a software implementation, this could be a server running somewhere, okay? But this device, of course, implements AES, but it does so in a way which has, in a physical way. And what happens that as it does its work, it gives me hints about what it's doing, about its internal structure. Specifically, in my case, I'm going to take a look at the power consumption, the instantaneous power consumption of this device every microsecond, and I'm going to output a power trace. A power trace is a sequence of, let's say, 1,000,000 points, and each one of these points is the instantaneous power consumption of the device while it's doing encryption at specific time. And now I have more information which I can try to use for my attack, okay? And if I write this as the formal definition of power analysis, as I'm going to use it in this work, now I have a description of a cryptographic device, plaintext and ciphertext, and power traces, okay? And I'm going to try to find the cryptographic key. What's nice about power traces? As I told you previously, what really causes problems for me, the attacker, when I only have the plaintext and the ciphertext, is the diffusion property, the avalanche property. What happens if I'm using traces, if I'm looking at two very adjacent periods in the power trace, they do not have the avalanche property. The diffusion between two close in time spots in the power trace are close enough together for me to be able to make an hypothesis at time t and check it at time t+1 without compromising all of the rest of the assumptions I have about the system. So power traces are very good for me, the attacker, when I'm trying to attack this device, okay? Power analysis has been demonstrated in 1996. It's well known that it works, okay? So what I'm trying to do now is trying to use this power trace in the scope of solvers. So what am I going to do, okay? Oh, before I do that, I'd like to say a few things about power analysis. I understand that a few of you have touched it. No, nobody's ever done it here? So power analysis in a nutshell. Okay, power analysis builds on the assumption that power consumption is variable. And not only is it variable, different instructions cause different power consumption, and different data cause different power consumption. And this means that the logical leap here means that I can do this, I can run this backwards. If I analyze the power consumption, I can make some inferences about the instructions in the data. What does this mean? Inference about the instructions means I can do reverse engineering. I can output the list of the instructions the device is performing. And inferences about data, specifically in my case, is key recovery. Okay? So because power consumption depends on instructions in data, I can look at the power consumption and learn about the instructions in the data. Now, at this point, I'm doing this talk and variants of it for a few years now. And I would have a few animations and pictures of transistors where I would use to prove you that power analysis, that power consumption is something which is dependent on instructions in the data. But now, fortunately, there is a revolution in the world, and it's much easier for me to prove this to you. And this is called a smartphone. Probably you have it. And this is a living proof that power analysis works. Okay, the smartphone has a CPU, it has a lot of sensors, right? It has radios, has accelerometers and so on. Let's ignore the sensors for a moment and the radios. It has a CPU, okay? And sometimes we take our smartphones and perform a CPU-intensive operation which has no I/O and no sensor. For example, we play a game, okay? Some of us play games on our smartphones. We can admit it, okay? And as we are playing this game on our smartphone, we feel that our smartphone gets hot, right? And the battery runs down, okay? Yes, Gideon.
I thought the 3D games spend an incredible amount of bandwidth and power downloading ads.
Yes, yes. About 3 times the amount of, 3 times the power they spend on the game, they spend on the ads. Yes, but it's kind of scary to think about that. But the whole thing only runs out to about $1 a year. If you just charge your computer all the year, it costs you about $1 in electric. But okay, so now I can give you a living proof that power consumption is variable. Okay, I just want to show this picture which I found online. Okay, so power consumption is variable. Okay, so I have this fact, it's established, and I'm going to do side-channel analysis with solvers. And okay, so now I'm trying to do cryptanalysis, and 2 groups, one of them in Belgium, one of them in Princeton, thought of doing it. They just used the cipher, and instead of feeding only the inputs and the outputs of the cipher, they also fed intermediate data, which is related to the power consumption. And of course, I'm standing here and I'm talking to you, so of course they were successful, okay? The result, the key can be recovered from the side-channel data. Great, great, okay, but as you see, there is a small but. And let's see if we can try and find the mine in this statement together, okay? The key can be recovered from the side-channel data if there are no errors in the side-channel trace, okay? So many of you are scope jockeys and have tried to measure physical phenomena using your scope. And as you know, there are never no errors in your scope measurement, okay? So this is the harsh reality of power analysis. Here is a very small device. Can anybody guess what this device does? Yes. This is an inverter. It takes a square wave input here, and it outputs a square wave output here, which is the inverse. This is an N-type transistor, and this is a P-type transistor. You can just go through it in your head, and you can see that a logical 1 here causes the 0 to run out here, and a logical 0 here causes the 1 to run out here. Okay, so now I'm going to feed the square wave input into here, and I'm going to take my oscilloscope, and I'm going to look at the output. Okay. And how am I going to measure the power trace? I'm going to take a very small resistor, let's say a 1 ohm resistor. I'm going to put it in series between the device and the ground, and I'm going to measure the voltage drop on this resistor. And the voltage drop is related to the power consumption. Okay? Now, what do we see here? When nothing is happening on the circuit, there is no power consumption at all. This is something which is a property of CMOS transistors, and we really like it. This is why we can use a small battery to power our devices for a long time. Okay? If nothing happens, there is practically no power consumption. And when the device switches from 1 to 0, there is a peak. Okay? Sometimes it's a big peak, sometimes it's a smaller peak. It's related to the fact that these capacitors, passive capacitors, get charged and discharged. Okay? I don't want to go into it. Okay, so if I was somehow tasked with performing power analysis of this device, this power trace would be beautiful for me. Okay? But the problem is that it never looks like this, right? What happens to the power trace when I really try to measure it? Okay? So there are several things which are going on in this device which cause problems for me. Okay? First of all, I'm not measuring only the cryptographic operation. Okay? I'm attacking a system. Okay? A chip or a decoder or a video set-top box. And this system is doing other stuff other than doing my encryptions. It might be doing, I don't know, I/O, it could be doing all sorts of CPU tasks, threads, and so on. What happens is that other stuff is going on in this device under test, and I'm obviously measuring not only my calculations, but also this. This is called switching noise. Another thing that happens, oh, sorry, I gave you too much errors here. I'll just bring it up slowly. Every piece of conducting wire on my device and connecting my device to the world is both a transmitting and a receiving antenna. And the electrons which are moving through the air modulate themselves onto these cables. And this is called electronic noise or thermal noise, because when you cool the device down, it gets weaker. And I'm obviously measuring this thermal noise as well, because I'm measuring what's going on the cable. And the third thing which is causing problems for me is that I'm using a physical device called an oscilloscope, which is connected using a physical device called a probe. The scope has its limitations. It has a digital analog to digital converter, which runs a certain amount of times per second. It has its own impulse function. It has its own sensitivities. It has this quantization. What happens at the end of the day is, instead of having this pretty exact representation of power consumption, I have this disgusting errored thing which we feel is difficult for us to perform power analysis on. And let's try to give this a rigorous treatment, okay? And this is called the information robustness trade-off. Let's take a rigorous look at this phenomenon we just saw. Okay, so let's assume I'm going to perform my solver attack. The solver needs a set of statements, and each one of these statements is calculated from a measurement. Okay, I take this trace, power trace, and I measure it. Let's say I measure it at 100 different times, and I feed these measurements into my solver system. Okay, so I have a measurement space which is 100 dimensional, and each one of these axes is the value of a certain measurement. Okay, is this okay? Okay, so here is the precise measurement. Okay, if there were no errors and no artifacts and no nothing, this would what I have measured, what I would have been able to measure using my test setup. And it has been shown in the works of the Belgians and the Princeton guys that this is enough to recover the key with actually very good accuracy and very high speed. Okay, and here is what I get on my scope. Okay, if this was the case, I would be very happy, because my actual measurement would be the precise measurement, and I would be able to output the key quickly and efficiently. But what happens is that these errors and things, or noise, you don't have to treat it as something bad. Error means that it's bad. Noise means that it's a fact of life. Okay, so what happens is this circle moves aside. Now what happens? Okay, I'm providing this measurement to the solver, and the solver looks at the equations and looks at this measurement, and what does the solver output? No, it says unsatisfiable. There is no key which can give out this measurement. Okay, the measurement space has a code word here. It doesn't have a code word here. So now looking at this picture, what do we immediately feel inclined to do to make this work again? We want to do this, right? We increase the robustness of the equation system. Okay. So we increase the robustness. We now say the equation set could be okay. At time t1, the leak is 3. Now we say, no, it's not 3. It could be 2 or 3, or 2 or 3 or 4, or somewhere, but it can't be 7 or something of the sort. And we increase this robustness until we get into, until the set of valid measurements includes the precise measurement. But what happens here is that the measurement space does not look like this, but rather it looks like this. Okay? And now what happens is that inside this circle of measurements which are validly represented by the side-channel measurement, there are exponentially many satisfying keys. What happens when the solver has exponentially many satisfying keys? What do we know what it does. It just brute forces all of these keys. Because all of these keys are legal, what happens is that the solver is again reduced to brute forcing. And this results, again, in an intractable running time. So this is what we call the robustness information trade-off. It's a very, very cruel trade-off. If we use an equation set which has errors in it, then the solver returns unsatisfiability, because the correct solution is not inside the set of measurement which I can accommodate. But if I increase the set of measurements, if I add robustness, then the solver runs for an intractable time. Okay? So this is where we were stuck at 2009. Either one of these is not good for us. We can't use solvers for power analysis, cryptanalysis in the real world. Okay, so again, it's a hard problem. So again, I'm an engineer. So if I have a hard problem, then I solve a different problem. Okay, so how can I change the problem to make it more acceptable for me? Okay, here is the solver. This is the tool I used previously. The solver receives a set of statements, and it outputs a satisfying assignment. Now, instead of a solver, I can use a bit of a more elaborate tool called an optimizer. Now, an optimizer works more or less the same way as a solver, but it doesn't receive only a set of statements. It also receives something called the goal function. And the solver, the optimizer, chooses among all of the possible satisfying assignments the optimal assignment, the one that gives us the best value for the goal function. Let's say I want to minimize the goal function, give me the minimal value of the goal function. And again, this is a general purpose tool. It's a bit more elaborate and heavy. It takes more time to run than the solver, but it's also very useful. One example where it's used, actually IBM has a group which wrote their own solver, and all day they sell usage of the solver to companies around the world, transportation companies, shipping companies, who want to optimize the routes. Okay, here is a classical application for optimizers, which actually is in the field today. I want to take the Russian railway system and I want to save fuel. Okay, I want to serve all of the stations in the railway system. I have constraints. A train cannot be present in two places at once. Two trains cannot be present on the same railway at the same time, okay? A train cannot travel, so on and so forth, before needing fuel. But I also have a goal function. The goal function is, please serve the schedule of the Russian railway system in a way which minimizes the distance traveled by the trains, minimizes the gas consumption of the trains, and so on. And when you save a lot of money using this tool, suddenly it becomes very, very important, okay? So this is an optimizer, and similar to SAT solvers, which are also developed in universities, and there's competition between every year. There's something called the SAT race, where people run their SAT solvers and see which one of the fastest. There's also something called the pseudo-Boolean competition, the solver competition, optimizer competition. Every year people compare their optimizers. It's an active work. People are actually researching them, trying to find the best way of doing it. So okay, how do I use this in my context? Okay, so if I go to the previous slide, I had this big circle, and my assumption was that all of the points inside the circle are equally eligible to be the correct key. So now my insight is that some mistakes are more expensive than others. What do I mean? I am going to give a price to each mistake I make. Okay, there is the correct measurement, which is not the correct measurement, it's the measurement I got. Every time I deviate from this measurement, I'm going to pay a price. And the optimization will be, let's try to pay the minimum price. And what's really nice is that I gave you this idea that there's a continuum of points, and the decoder which receives this trace outputs a point on this continuum. This is not correct. Actually, the decoder is a bit more elaborate. It's something called a soft decoder. The decoder for each one of the points along its axis outputs an a posteriori probability, which means how likely it is that this specific point is the one that was transmitted, conditioned on the fact that this trace was the one received. Okay? If somebody here did some signal processing work, this is a Bayesian decoder, a naive Bayesian decoder. Other decoders also exist. Okay? So I can give a price to every mistake I make, and I want to do the best I can. Okay? So here is my new definition of side-channel analysis based on solvers. Okay? I have a description of a device. I have plaintext. I have ciphertext. And now I need to find the key that minimizes the estimated error. Okay? So once I output a key, I can run this backwards and say, if this is the key, then this is the power trace that should have been if there were no errors. I want the power trace that should have been to be closest as possible to the power trace that I did see with my scope. Okay? So now let's take a look at what really happens if I do this. Okay? Again, I'm going to look at the measurement space. And this is a real measurement from my lab. Actually, it's based on a simulation of a device, but this is real data I used. Okay, I'm just going to look at 2 dimensions of this measurement space. And the brightness of each point is correlated to the likelihood that this is the point which was really received. Okay, so there are lots of points here which are non-zero. Okay, and if you would shut down the light, you would see them also less likely points here. Where is the precise measurement? Wow. Yeah, you see it? Great. Can I have lights again, Matt? Wow. Matt, you're awesome. So let's just take a look a bit closer at the points here. And where is the precise measurement? Here it is. Okay? This measurement It's the 680th most probable of the 65,000 points here. So it's pretty likely, but it's still exponentially difficult to find it. Okay. Now I just gave you two measurements. Okay. I don't give you 2 measurements. I'm going to give you 100 measurements. Okay. So if I didn't, if I would try to brute force over all of these measurements, I would have to do an exponentially crazy amount of evaluation to see if it's the correct one. But now if I have a ranking by probability, I still have to do a crazy large amount of exponential work. Okay? And practically, in my measurements, the average rank of the correct byte out of 256 possible candidates, it's number 14. Okay? So 14 to the power of 100 is still a lot of work. But the thing is that these points now are not IID. And this is the real trick here. Because I also gave to my solver the description of the cryptographic process which is creating these bytes to be output. Okay? So if one of these measurements is the input to subbytes, and one of them is the outputs to subbytes, as soon as I assume one of them, I also have to assume the other. Okay? So what this means is that this point might be quite unlikely, but it's really powerfully suggested by other information I have. And as I said, because of this slow diffusion property, what I saw a minute before, what I'm going to see a minute after, is going to really affect my choice at this stage. Okay? So I'm just going to go a bit into the tool I used, which might be useful for you in other applications. The specific optimizing system I used is called the pseudo-Boolean optimizer. And this is how it works like. The objective of the pseudo-Boolean optimizer is to output the vector x of variables, which minimizes this goal function. Okay, this is a constraint function called c. I multiply it by x, I get a number. Okay, I want to minimize this number, subject to this matrix of linear constraints. A times x has to be greater or equal to b. And why is this called the pseudo-Boolean optimizer? Because the variables themselves are Boolean, but the coefficients of A are signed integers. Okay? So if you've delved a bit into logic systems and so on, you know that the simplest logical system we use are SAT statements. SAT statements are Boolean and Boolean. And on the other side, there's something called integer programming, where the variables themselves are integers and the coefficients are integers. So this is somewhere in between. It's a compromise, which is very good for me because this simplification makes the solver quicker and it makes the implementation more easy to use. Okay, so using very simple to describe gadgets, I can turn a linear pseudo-Boolean optimizer into a nonlinear pseudo-Boolean optimizer. And this is using the classical linearization technique, if you know. Okay, so if I have a constraint, let's say y is x1, x2, remember that y and x1, x2 are Boolean. Okay, so what this actually means is that x1 plus x2, if both of them are 1, then y has to be, okay, more or less this, okay? I'm not sure I wrote the statement correctly, but there is a linearization system, and you can use nonlinear, and you also can multiply these variables together, and you can also use their inverts. So this language is very expressive. I can very easily describe to you a pseudo-Boolean instance. You can look at it and understand what it does. And this is in contrast to SAT systems, which are really, you need to be somebody who can understand assembly language to understand what SAT system. Here is a sample pseudo-Boolean instance written in the open pseudo-Boolean programming language. Okay, what do I try to do? What am I trying to do here? I'm trying to find the vector x1, x2, x3, which minimizes this goal function. Okay, and it has this constraint. Okay, x1 plus 2x2 plus x3 is greater than 2. Okay, so let's try to see if we can find in our heads the optimal assignment. Let's try the all zeros assignment. Okay, the all zeros assignment gives us the goal function of 0, which is really great, but 0 plus 0 plus 0 does not satisfy the constraint. Okay, so that's not good. Let's try the all ones assignment. Okay, this gives me 4. 4 is more than 2. This is great, and the goal function now is going to pay the price of 5. Okay, can anybody looking at this equation system give me the optimal assignment? 101. Precisely. 101, very well. This gives me a price to pay of 2, and 101 is 2. 2 is equal to greater than equal to 2. Great. Okay, this language is very expressive, and it's very rich. Okay, what do I mean rich? It's really useful for my application. Specifically, I'm trying to find the variables, my variables, which are either the inputs, the outputs, or all sorts of internal state evolutions of my device. They're all flip-flops. Flip-flops can either be 0 or 1. So it's really great that the variables are zeros and ones. On the other hand, the measurements, which are the things I provide to my system, they're sampled on some continuous axis, but I can sample them into integers. So the constraints, it's really great that they're integers, okay? And the nonlinear notation is rich and expressive enough for me to be able to write very elegantly and succinctly the things which are you can see in crypto devices. For example, here are some very simple pseudo-Boolean statements. Here is a negative OR, you see. Out is equal to not x1 times not x2. Okay, it's pretty trivial, okay? You can see this is a negative OR gate. Here is an exclusive OR gate. This is a bit cute, okay? I wanted to put this here because you see that I'm actually using here a nonlinear, I'm using here the pseudo-Boolean, okay? This integer. If you would write the truth table for this thing, you would see that this is exactly the exclusive OR statement, okay? You can just play with it in your head. Here is a bit of a more disgusting function. This is the key lock ciphers nonlinear feedback function. It's 5 inputs, 1 bit output. There's no efficient algebraic representation of it. But as you can see, I wrote something here which is a pseudo-Boolean representation of it, okay? And also, the goal function is really good for me, okay? The goal function, let's say I'm trying to determine the cost, the price of I'm going to guess, I'm trying to do a side-channel analysis. I guess that the key is a certain vector, okay? Now, choosing the key forces, of course, all of the internal values of the state to be also strictly defined. So now I have, for each one of these internal values, a chosen value, and I know the a posteriori probability of each one of these values. I want to find the overall probability that this is the correct value. What do? I multiply all of these together, and I get a single value, which is yes.
There's a negation missing someplace. Max doesn't become a min unless you negate someplace.
If the max is less than 1, all of these products, all of the a posteriori probability is always less than 1. So the log of a number less than 1 is negative.
Yeah.
So I want the minimum sum. It's the minimum. It's like entropy. Okay.
You want the maximum. It's a negative number, and you want
I want to maximize the negative number. Yes, yes. Thank you, Gideon. Right. Okay. So here is another example of a pseudo-Boolean instance. Here I have a vector x. Okay. You can just look at it. It's so apparent to see what I've written down here. X can be either 0, 1, 2, or 3. Okay. This statement means that only one and only one of these variables can be true. Okay. And x is an 8-bit value. Here are the 8 values of x sub 1 to x sub 7. And as soon as one of these events happens, it forces all of the other events to get their value. And these are the constraints. And here is the goal function. Okay, the goal function means that if you're going to choose 0, you're going to pay a pretty low price. If you're going to go ahead and say that x is 3, you're going to have to be pretty sure of it based on other evidence before you can go ahead and choose x is equal to 3. So as the solver, as the optimizer works, it will probably try first x is 0 and then move down this list. Okay? But again, because x might be determined by the previous value in this decryption, the former value in the decryption, it will do a bit more efficiently. But this is how my equation system looks. Any questions about this? Because now I'm going to describe my workflow and my results. Okay. So, yes, please.
So I'm wondering how you get the expected trace. So do you have a simulator, or do you run?
Okay. The way I prepare my decoder, it's a method that's well known in the art. It's from a paper of 2005 called Template Attacks, which is very, very interesting. It basically, you take your device under captivity, and you force it to output values which you would like it to output, and you measure. Let's say you want that value number 2 would be 5. Okay, you make it output value many traces in which value number 2 is equal to 5, and you find an interesting point on this trace, or a few interesting points, which are highly correlated with the value you are measuring. There are statistical tools which assist you in finding this point. And then for this point, this interesting point, you create a mean and standard deviation. And the mean and standard deviation are the mean and standard deviation conditioned on the fact that you were expecting 5. Okay? Now, for all possible values, 256 values, you create 206 means and standard deviations. Okay? If you're using, for example, 2 interesting points, you also have a covariance matrix for each of these. So now I have, if I get a trace which I don't know, I can use these variables, these means and variances, to create 256 probabilities. Probability of this trace conditioned on 1, conditioned on 2, conditioned on 3. And then using Bayesian inversion, I can flip this around and get the probability I'm looking for. Okay? Okay? It's really interesting signal processing, and the paper describes it much better than I just did. Okay?
I get that.
Okay? Well, good for you. Okay, so here is the workflow. I have this device under test. I'm going to do something novel to it, which will end up in the optimizer outputting the secret key. Okay? So what is my workflow? Itasca, by the way, is Tolerant Algebraic Side-Channel Attack. Tolerant because I can tolerate errors. Okay? So first of all, I'm going to take my device under test and subject it to reverse engineering. Okay? This can be based on prior knowledge. This could be based on really probing and so on. And the output of this would be the power model. A power model means that I am going to write a set of constraints which say if the device is doing this at time, is doing something at this time, then I expect its power, its precise power, to be this. Okay? And this is output from reverse engineering. And I'm also going to take traces, or let's say one power trace, which is output from the device as I am attacking it, and I'm going to put it into this decoder, this Bayesian decoder, which I just described. And this decoder is going to output a vector of a posteriori probabilities for each one of the measurements I'm going. So I get, let's take a look at the amount of data I'm using, the data complexity here. I have a single trace, for instance, and in this trace I'm going to take 100 interesting points, okay? And each one of these interesting points is going to cause the output of a vector of a posteriori probabilities, okay? So from this one trace, I'm going to get, let's say, 100 times 256 a posteriori probabilities. And then I'm going to put this into the optimizer, okay, these together, and it's going to run, and it's going to end up in a paper, and I'm very happy, okay? We know how it works, right? Our objective function is very well defined as researchers, okay? So let's talk about a real attack, okay, and the results. By the way, this is going to appear in CHES 2012, a month from now. So the solver is Skip. Skip is an open source solver written by ZIP, the Berlin University. It keeps running in these Skip competitions and these pseudo-Boolean competitions and winning, so it's pretty good. And the cryptosystem I'm attacking is a simulation. It's not a real lab device, but rather based on measurements which have been performed by my Belgian colleagues. So it's real data, but it's created by a tool which outputs simulated data. Okay? I don't want to make any groundbreaking claims. I didn't break a physical device yet. Okay? And what I did, I took a single power trace and I extracted 100 measurements from this single trace. So single power trace, data complexity is 1. The signal to noise ratio is reasonable. At 10 dB, it means that there's 10 times the amount of power in the signal than there is in the noise. This is a reasonable signal to noise ratio. I put these instances, I created a lot of these instances. I said I have a tool that creates them. I took 200 of these instances, and on average, in about less than 10 minutes, the key was recovered with perfect success rate. Okay? Okay? One trace, 10 minutes, 100% success rate. Okay? What does this mean? Okay. Before I describe what it means, I want to tell you a bit about the field of power analysis. Power analysis has been something which people in the academic world know about since '96. And it's well assumed that government agencies and so on and so forth know about it from World War II and on. Okay? So people know that power analysis attacks work. But what happens is that the most power analysis attacks until this day are based on statistical methods. What it means that you need many traces, and you try to make a hypothesis on these traces, which will cause them to behave in a way which, for example, you can split them into two bins. If your assignment is correct, if your hypothesis is correct, then these two bins will be statistically significant. Or there will be a correlation between your hypothesis and the traces at a certain amount of time. So and another thing which all of the previous, not all of them, but many of the previous attacks assume is that there is a linear correlation between the power consumption of the device and the data it is processing, okay? Which is, this we know because it's a CMOS device, okay? So how do you break power analysis? How do you make a device resist power analysis? You attack both of these venues. First of all, you try to make your protocol, you try to make your environment so that the keys are changed with high frequency. They're always fresh. So you won't be able to get a lot of measurements. So your statistical methods will fail. Or you can just inject noise to make the statistical correlation weaker. Another thing you do is you try to make all sort of electronical engineering tricks to break the linear correlation between the power consumption and the amount of bits which are flipping at a certain time. You can do this by, for example, what's called dual-way logic. You create your circuit, and then you create a mirror image of the circuit, and they always do the opposite from one another, so you really don't know what's going on. Okay? But what happens is that both of these assumptions, which make today's resistant devices resistant, do not hold when I'm using this new attack. First of all, crypto devices don't need high data complexity to be attacked with this thing. Okay? The data complexity is 1. And if I really have a lot of noise, I can average two traces together. So the data complexity is 2. Averaging really hits the signal-to-noise ratio. Okay? So I don't really need to average. If I average 16 traces together, I can do a great work in reducing the signal-to-noise ratio. So the data complexity is very low, which is something which previous countermeasures assumed would make them resistant to power analysis. Okay? Another thing is that I don't need anything particular about the leak. As I told you, I make no assumption about the leak. I leave this problem to the author of the decoder. Okay? The guy who writes the decoder, he can, as long as he can output a vector of a posteriori probabilities, that's enough for me. Okay? So if the leak is linear, that's fine. If it's nonlinear, okay. The device I told you has a nonlinear correlation between the Hamming weight of the byte and the power consumption. But there is a relation. Okay, so anything that I can write a soft decoder for, and it doesn't even have to be power consumption. It could be anything exotic, anything else. As long as I can write a soft decoder, I can do this attack. Okay, so these two facts together call into question the security of previously safe devices. Okay, so if you say a device is resistant to power analysis, you might have to go and check this claim again. Okay, so I think this is pretty exciting. Okay. I still don't have any practical devices I've attacked because it's a very fresh result. But I feel there's a lot of things that will have to be questioned if this really turns out to be practical. So where do I go from now? Future work. Okay. First of all, I used only power analysis and decoder. So I feel that anything that leaks can be attacked. So a nice thing to do was to try different things which leak and try to feed them into my solver. What I do know, at least I feel it, that if I throw garbage at my solver, which means low quality data, it knows to ignore it more or less. So if there is a measurement where all of the values in these measurements have the same probability, the solver will just ignore it. Okay. So I really feel that the more data I throw at the solver, the more effective it will be. Okay. The second thing is different leakage models. Again. I can try different things. For example, I can try to use cache timing, electromagnetic leakage, and so on and so forth. And the third thing, I touched on it briefly. The decoders we currently use have this very elaborate pre-processing phase where I have a captive device, and I do profiling, and I create these vectors. And then I have a very small data complexity. I only need one trace, and I use this trace and I get the key. So it might be that I have limited time with my device. it might be possible to use less profiling time and more traces for the attack, and still get an attack with low data complexity both in the online and offline phases. Okay, and the fourth thing, which is really apparent, is to get a real, let's say, smart card or car or a computer and attack it using this method, which is really something interesting to do. It's a bit difficult. Okay, so this time I thank you, and you can get the paper from this website, and I'd really welcome any questions or comments. Okay, thank you. Yes, please.
So, I don't know if this is really within your mandate for what you're interested in, but what would be the characteristics of the device that could defeat this attack?
Let's see. I would say that what I really need is diffusion. I need low diffusion. So a device which has lots of diffusion would defeat the system. Okay. So if, for example, if I make a guess, and to check this guess I would have to go over a whole space of solutions, that would make my device difficult. One example is, for example, a device which does a lot of things in parallel. Okay. So I have to make a lot of guesses at the same time. Okay? Anything else?
How does the attack scale with higher complexity cryptosystems?
What do you mean in complexity?
So say we make the bit size larger or something like that. I mean, so AES, much bigger keys or something. Is it just...
AES doesn't use a different round structure for larger keys. It just does it more rounds. So AES with a larger key is not more powerful when I attack it using this way.
It's just doesn't change at all.
With the exception of TV decoder cards, who in his right mind puts his secrets where the other guy is getting within 2 inches of them with a scope?
Oh yeah, that's true. That's true. If you can always say that if you have physical access to a device, then you're screwed anyway. Okay. But first of all, TV decoders are a very interesting market. And the second thing is that now we are taking our cell phones with all of them secrets and touching them to all sorts of, we at least want to do it once the software and hardware is in place. We're going to go and touch, places you wouldn't touch with your hand, suddenly you're going to touch with your phone. And who knows what's on the other side. And the third thing I can say is that if you're using electromagnetic leakage, suddenly your range is much larger. Okay? Pyroanalysis does always have this, this comment you have to make that to do pyroanalysis you need a power trace. Yes. Okay? Anything else? Okay.
Okay, let's thank you.
Okay. Thank you. Thank you for the.